Especially today, no one showed up.
Hey guys, I think I'm gonna go ahead and get started here. Welcome to a new week and hopefully you guys are all doing well. I noticed that the clock now in this room is correct. With the time change, did you all survive with one less hour of sleep on Saturday night? That's what I always hate that, but then I like having the daylight at the end of the day. So I have to say I'm happy about that. So now we've got this clock correct and every other clock in the building is now wrong. They just don't get them all fixed at the same time. So anyway, I had an interesting weekend, as you know, well, I was here late Thursday night and left very early in the morning on Friday, and I headed out to the airport. I was going out of the Ontario airport, going up to Seattle. I was going on a flight to Seattle. I had to stop in Las Vegas on the way. Sitting there 30 minutes before the flight's gonna board. And somebody behind me said, "Oh, hi, Dr. Annan." And I was like, "What? There's somebody here." And I found out Crystal was also going on the same plane. Not all the way to Seattle, I guess. You went to Portland?
Yeah.
Okay, so she went to Portland, but I couldn't believe it. I was like, there's like 5 different airports in Southern California. And what are the chances? Who else would be crazy enough to take a 5 a.m. flight out of here? But yeah, so 2 people in this room were on the same airplane on Friday morning. That was really quite a coincidence. Anyway, I had a pretty eventful weekend. I tried to climb a volcano up in Washington and got totally whited out about 1,000 feet below the top of it. So, you know, this is what happens with this hobby. Sometimes it works out and sometimes it doesn't, but you know, you miss 100% of the shots that you don't take. So I had to go give it a try, and I'll just go give it another try, I imagine, at some point down the line. So anyway, I'm a little tired because I stayed up there over the weekend, partially because we weren't sure exactly when we were gonna go try to climb this mountain. And so I went to bed last night after my office hours and woke up today also at 3 a.m. So I've been up already for almost 11 hours, and I flew back, got back about 2.5 hours ago and raced over here. So I'm hoping this won't be too ragged. By my standards, I usually try to keep my notes really polished and good, but bear with me if I'm a little bit off my game today. We'll just have to see how this goes. Also, just a reminder, I do have office hours later today. The later you wait to come to my office hours tonight, the less sense I'm probably gonna make. By the time we get to midnight, it might as well be in Chinese. So if you have questions for me, I would recommend try to get me earlier. I'll be around after class and then also starting at 8 o'clock. And 8 o'clock will be a whole lot more coherent than 11 o'clock tonight. I have a feeling. There is homework due, so don't forget about that. Homework number 8 is due tonight. And I noticed one person's already turned it in, but there's still time to ask questions on that or collaborate with myself or your classmates on it if you need any help on any of that. The next homework is also in Canvas for you already to go. It'll be due next week on Tuesday. So we're kind of in this once a week homework cycle right now with Tuesday assignments coming up. We're about 2.5 weeks out from our midterm. Our midterm is actually right before spring break. So don't be surprised if I decide to have a quiz maybe next week. And also if I put together a resources folder for that midterm. I need to get my head together and figure out exactly how I'm gonna do all of that. Probably have some review sessions again, yada, yada, yada. The same old stuff that we did first time around. But for the immediate future, just this homework is what you have to do for tonight. Anybody have any questions about any of that? Not so far. Okay, great. If not, remember that last Thursday we did finally get started into chapter 4, and we're talking about limits of functions right now. So I've recapped here in this big box the underlying definition for what it means for the limit of f of x to equal L as x approaches c. Now, in this definition, I'm assuming that L is a real number. You might remember that last week I had allowed for plus or minus infinity to be the value of the limit of the function. I'm going to come back later and talk more directly and explicitly about limits at infinity, just like we did for sequences. I'm going to do the same thing for functions. So for the time being, for most of what I'm going to do today, let's just imagine L is actually a real number. Because you can see here, for example, I'm going to try to take f of x minus L. I couldn't do that if L was infinity or minus infinity. So this definition is definitely restricted to real values of L, okay? And it's kind of a word salad of Greek letters here that you have to get comfortable with. And everything has to be exactly in the right order with exactly the correct quantifier for it to actually make sense, right? So for all epsilon greater than 0, which means in terms of my picture, by the way, for all blue strips that are buffering around L, plus or minus epsilon around L, for every one of those, right, for all epsilon greater than 0, there exists a delta greater than 0. That's going to be the vertical red strip, right, that goes from C minus delta to C plus delta. So it's centered on C, right? So for all epsilon, for every blue strip, I can make a red strip. That's basically what it is. Such that, excuse me, if I look at any x value within the red strip other than C itself, notice that this x minus C is not supposed to be 0. It just means that x is not equal to C right there. So if I take any point other than, you see I put an open hole right there, this f of C value could be anywhere and it won't affect this definition. But for every other point, I'm trying to draw it thick right here, guys. Every other x value that's within the red strip spits out an f of x value that's in the blue strip. That's basically how it works, right? So that's what this says on the second line. If x is in the red strip, then f of x is in the blue strip. It's basically just how we're saying it in words. But obviously, in your proofs, you're not going to be just doing proof by picture. You're going to need to use these absolute values and the formal definition. Okay, we did 2 or 3 of these already last week in class to kind of get warmed up with it. I want to warm up a little bit more today and do one more. Before I do that, though, does anybody have any questions about the picture here or just what the definition means? Does it seem reasonable? It should match up with your intuition about limits that you learned in calculus, which is that as x approaches C, you don't actually care what happens at C. So the f of C value is actually completely irrelevant to what this limit value of the function would be, right? So the L value there. Okay, so let's just come over here and try a warm-up problem. Let's try to show that if we take the limit of 1 over x as x approaches C, that will be equal to 1 over C, okay? And this will be for all C greater than 0. Let's just assume that C is greater than 0. It's also true if C is less than 0, but it's just a similar proof. So let's just do this one and see if we can make sense out of it. Okay, so let's get started on this warm-up here. Let's try it together. I'll try to go slow since it's been a few days and since I'm still trying to get myself back in the hang of it here. Looking at this definition, the first thing we come across is for all epsilon greater than 0. So I'm going to start here with let epsilon greater than 0 be given. Okay? And the next thing that we would generally write in our proof is we would then have to come up with the delta. But usually figuring out the delta is where all of the heavy calculation is, right? That's where the hard work comes in. So I'm going to do that over here on some Scratch. So you saw me do this last week, and it's the same idea today on this one. We're going to write out some Scratch work, basically taking the f of x minus L less than epsilon and kind of working backwards to figure out what the delta should be. Okay, so you're kind of going to reverse engineer this thing. So let's just write that down. F of x minus L less than epsilon is where we're hoping to end up eventually. And I'll just remind you guys that in this scratch work, you should use these arrows and make sure they're pointing in whichever direction is correct, or possibly both. In this first step, I'm just gonna write in f of x, which is 1/x. And I'm gonna put in the L value, which is 1/c in this case. And we want that to be less than epsilon. Okay, so just plug all of that in, shouldn't be too big of a deal. And let me get a common denominator on this subtraction of fractions that we see here. So on the left side, if I make a common denominator of cx, then I'll get c minus x on top, right? So I think that's the same thing as 1/x minus 1/c, less than epsilon. And of course, I ultimately want to see absolute x minus c showing up. At the moment, I have absolute c minus x, but see, it's the same as absolute x minus c. So one thing I can do is I can rewrite that numerator as absolute x minus c. And the other thing I can do if I want, on the bottom, I can take the c out of the absolute value bars because they did tell us that c is greater than 0. So I don't really need absolute value bars on anything that's already positive. Okay, and so this is where we are at so far. And if I solve that for absolute x minus c, I would get c absolute x epsilon. I think if I did that right. And this is where we run into a problem, and we had this problem last week on one of our examples as well, which is that you'd like to make this your delta. Because, right, that fits with the form here, absolute x minus c less than delta. So you'd love for this to be your delta, but the problem is that your delta has to be a constant. So it could depend on epsilon, and it could depend on, in this case, the c as well, both of which are fixed constants, but it should not depend on x, right? The delta should not depend on x. And so what we did last week, if you remember, when we had a problem where that showed up, is we did this preliminary delta, where we sort of decided to get a restricted range on x on a preliminary basis, and then looking at the range of x that we had, we sort of figured out what a valid choice of delta would be. Okay, so I'm gonna do the same exact thing here. The same exact thing here. Let me actually, maybe I can just do it right along with the scratch work here as well. Let me draw my little picture here with what do I want to actually have here? I'm gonna put 0 on my picture, and I'm gonna put c right here. Okay, so c is greater than 0. And I want to come up with an interval. Now, you might remember on the example I did last week, you don't need to write this down because it's already in your notes. We had something where it was limit as x approaches -5. So what I did is I put -5 on my number line, and then I just said, oh, let's just start off with delta to be 1. And so what we did is we created an interval that went from -6 to -4. Don't know if you remember those specific numbers, but that was the idea behind it that we had on that example last Thursday. Now, the trouble with this problem, though, is if I just try to say, well, let's just let our delta, our preliminary delta be 1. I actually don't know how close c is to 0. And it might be that c is very close to 0. And in that case, if I was drawing an interval of radius 1 around c, it might actually include 0. In other words, you would be looking at x's where you could have numbers that are 0 in for x, or very close to 0, which would sort of blow this fraction up to infinity. It's never going to be less than epsilon in that case. Okay, so on this particular case, guys, instead of choosing a sort of a preliminary delta of 1, like we did last week, what I'm going to do here is I want to make 100% sure that the x's that I'm going to be looking at in this domain are well away from 0. And I can do that if I allow a c/2 radius here. a C over 2 radius. That will force X to be limited from, what is it, C over 2 to 3C over 2. Okay, so let me write this down in the notes then. Choose a preliminary delta of delta, let me just call it, say, delta 1 equals C over 2. So that X will be between C over 2 and 3C over 2. Now again, C over 2 is not the only correct answer. You could choose, C over 3, C, 0.7C. There'd be lots of things you could choose. Just make sure, the main thing here, guys, is to make sure that your interval does not pass over 0. You do not want X to be 0. And if I'm limited to this interval right here with my X's, then the smallest my X can be is C over 2, and the largest it could be is 3C over 2. Remember, once we get our final delta, we're going to assume that the distance from X to C is less than that delta. So already at most, our final delta will be C over 2. Do you guys remember this? We're going to take a minimum, right? Well, our final delta is going to be a minimum of this preliminary delta and something that might make it an even smaller interval. But at worst, the interval is this big. And if it's this big, we're okay, because the X values will be between C over 2 and 3C over 2, which isn't too bad. We can kind of control that pretty well. Okay, so let me continue over here, and let's talk about what happens when X is between C over 2 and 3C over 2. Okay, so then obviously 1 over X is going to be positive. So X is already positive. You can see in this interval, X is positive. So 1 over X will also be a positive number. But 1 over X will be less than 2 over C. Guys, if we flip this over, if we take reciprocals of everything here, 1 over X will be less than 2 over C. So that is helpful. Now, why am I looking at 1 over X, by the way? I'm looking at 1 over X because look here, look at what I have here. I have a 1 over X that I'm going to want to control in this inequality. That X is in the denominator there, right? So let's just keep going. Thus, if 1 over X is less than 2 over C, and greater than 0, sorry, then what can we say about absolute X minus C over C absolute X? So just looking at this one, guys, right here. Right. Let's just see what we can say about it. This is less than, so absolute X minus C is on top. On the bottom, I have a C, but I also have 1 over X, which is 2 over C, less than 2 over C. Okay, so it's going to look like that. And right, so in other words, if this is less than epsilon, then so is this, right? I've replaced this thing here, which has an annoying X in the bottom, with something over here that has only constants around the X minus C, right? This is the whole idea, right? The whole idea is your delta cannot have X's in it. This X right here is kind of a problem. So what I'm doing is I'm getting rid of that X by replacing 1 over X with something larger. And I am now going to say that, so then let's just note that, so then absolute X minus C over C absolute X less than epsilon, that is implied by absolute X minus C times 2 over C squared less than epsilon. If this one is less than epsilon, then so is this one, right? And if this one is less than epsilon, then we can retrace our scratch word. which is what we wanna do. We wanna retrace that scratch work. So we want this to be true, guys. This is what we would like to have true. And what I've done here is I've said, well, it will be true if this one's true. Right? And this one is equivalent to absolute x minus c less than epsilon c squared over 2. Yeah. So I've solved for x minus c here. And now this, my friends, is the delta that we want. Keeping in mind that we've already chosen a preliminary delta. But now combining that with this new delta that we have over here, we should be good to go. Let's come back to the main proof now. And what I'm gonna do is I'm going to let delta be, is it min or max?
Min.
Min, very good. It's always min of the original delta, which was c over 2. And the new delta that shows up on the right-hand side of our scratch work way over there, which is epsilon c squared over 2. This is the delta that we're going to choose. And now we just have to check. Once we write down the delta, we just have to check, does this definition hold? So let's check it. Let's assume that 0 is less than absolute x minus c is less than delta. That's the starting point here. And I want to show that absolute f of x minus L is less than epsilon. Okay. So in this case, thus, absolute x minus c is less than both of these. It's less than both of these, less than c over 2, for example. So c over 2 is less than x is less than 3c over 2. So that was basically just going back to our scratch work again. Okay. And so 1 over x is less than 2 over c. I'm kind of just repeating that scratch work into my proof now. So, yeah, so absolute x minus c over c absolute x. What can we say about that? I want it to be less than epsilon. I want this to be less than epsilon so that I can retrace my scratch work. Let's take a look at this, guys. First of all, I can certainly tell you that, well, I can tell you that, I guess I'll add one step here. I can certainly remove the absolute value bars because x is already positive for sure. And then you see the 1 over x here? The 1 over x is less than the 2 over c. So absolute x minus c over times 2c squared, basically, is what we're gonna get. And that is less than, let's just finish it up here, sorry. That one is less than, just a second, I want it to be less than epsilon. Why is it less than epsilon? It's 2c squared absolute c. Yeah, sorry. So this is, let's recopy the 2 over c squared here. Absolute x minus c is less than delta, right? And delta is less than epsilon c squared over 2. So I can replace this with epsilon c squared over 2. So that is exactly epsilon. Right, so now I can retrace my scratch work from there. So I've erased part of the scratch work, unfortunately, but now we retrace the scratch to get absolute of f of x minus L less than epsilon, and that's the end of the proof. So that's basically it. Yeah, see guys, you have to use both of these. You have to use both of these. You use the c over 2 to first put this limitation on x, right? delta is less than C over two, so that means that one over X is less than two over C. We need that. And then we later use the other bound on the delta, which is this epsilon C squared over two, to substitute for absolute X minus C right here as well. So it takes a little bit of finagling, a little bit of work to get that to come through, but it does, it works out very nicely. Okay, seem okay? I mean, some of the details are a little intimidating. I know when I first was learning how to do these, I found this preliminary delta thing, followed by then having to refine the delta to be a little bit haphazard. I didn't feel real solid on it until I practiced it a few times. So might have to do that. Okay, well, if you guys are all right with that warm up, I'm going to state the limit theorems now for functions. We had limit theorems for sequences, and we're also going to have limit theorem for functions as well. Let me put that over here. This is actually in the book, it's proposition 4.7. And give yourself plenty of room to write this down because there are several parts to this. It's going to take a little bit of writing. So I'll just say here, we can call this the limit theorems for functions. Limit theorems for functions. Okay, that's what this proposition is going to be. So here's the setup, guys. We're going to let f and g be functions from a domain D to the real numbers. So D is just going to be my domain. So just where D is some subset of the real numbers. And then we're going to let C be an accumulation point of D. So C is going to be, doesn't have to be in the domain, but it has to be an accumulation point of the domain. So every neighborhood of C has to contain points of the domain. So C is an accumulation point of D. Then here is our proposition. If the limit as x approaches C of f of x is equal to L1, and the limit as x approaches C of g of x is equal to L2, then I have three statements here. So 1, 2, and 3. This takes an entire board just to write this down. Okay, the first one is that the limit as x approaches C of f of x plus g of x. You add the two functions together and you want to know what's the limit of that. Well, you won't be surprised to learn that the answer is L1 plus L2. You just add the individual results. The second one is for multiplication. So if I had the limit as x approaches C of f of x times g of x, well, that would just be L1 times L2. Just multiply the results. And the third one would be the limit as x approaches C of f of x over g of x. So if I took a quotient of these two functions, then this one is L1 over L2, but we have to add a little proviso here, and that is provided that L2 is not 0. We have to make sure that that is not 0. Okay, great. So this is very similar to the result for sequences. I think in the case of sequences, though, there were 4 parts, and that was because for some reason the book decided to create a separate part for just a constant times xn. But if g of x was a constant function, then this item number 2 could be viewed as just being a scalar multiplication of f of x, and it would apply to that case. So we don't really need 4 parts to this proposition. 3 is really going to be good enough. Okay, any questions on the statement there? We have a lot to prove, but do people understand the statement at least? Seems okay? All right, let's try to prove a little bit of this. And I may do not all of it. we'll try to prove some of this, and get the feeling behind it, kind of how it works, and then I'll probably call that good. The first part we should definitely do though. Oh, and by the way, I should also mention that subtraction is also included with addition, because you could just take your g of x and replace it with a negative g of x, which is just as good of a function as g of x. And then you've got subtraction covered. So this covers addition, subtraction, multiplication, and division, if you're wondering, okay? But let's do the proof of the first part. Okay, so proof of part one. Start with this one. So we're proving a limit, right? We're proving the limit of a function is equal to a particular value, and we've got our definition right here, right? Definition says for all epsilon, prove that there exists a delta. So we're going to start exactly off the same way we always do. Let epsilon greater than 0 be given. Okay? Now, on all of the concrete problems that we've done up to this point, we would now go off to the scratch work to sort of solve for the delta. But see, in this case, we already know that we have a delta for the f of x part, and we also have a delta for the g of x part. They might not be the same delta, but I have deltas for those limits ahead of time, and I'm going to bring them into the proof right now. So I'm just going to say here, guys, since the limit as x approaches c of f of x is equal to L1, there exists a delta 1 greater than 0 such that if 0 is less than absolute x minus c is less than delta 1, then absolute f of x minus L1 is less than anything I want it to be less than. And wondering if everybody has an idea what I want this to be less than. Yeah, good thinking. We're thinking ahead a little bit. We're gonna need to use an epsilon over 2 here. That's because we are gonna have two different two different statements, one for f and one for g, right? So let's just say similarly, there exists a delta 2 greater than 0 such that if 0 is less than absolute x minus c is less than delta 2, then absolute g of x minus L2 is also less than epsilon over 2. So pretty much carbon copy of the first line, but now we do it for the second function. And what do you think my final delta is going to be? The minimum of those two deltas. Exactly. So I'm going to set delta to be the minimum. So all of chapter 3, we kept taking maximums of n1s and n2s. Now in this chapter, we're taking minimums of delta 1s and delta 2s, right? But the minimum of those two deltas is definitely a number greater than 0. And I just need to verify that it does work. So I'm going to assume now that 0 is less than absolute x minus c is less than delta. And what I have to try to show you is that, what are we trying to show? We're trying to show that the limit of f of x plus g of x is equal to L1 plus L2. So in this definition, where I have f of x, now I got to put f of x plus g of x. And where I have L, I'm going to replace it with L1 plus L2. So let's take a look at that. Let's take absolute value of f of x plus g of x minus the quantity L1 plus L2. Okay, so this is what we would need to look at, and we want this to be less than epsilon, okay? So guys, this is a sort of argument we've seen 3 or 4 times. I would expect everybody in here to be able to do this. Essentially, what you're going to try and do is break this apart into 2 pieces using the triangle inequality so that you can incorporate both of these inequalities just directly into the triangle inequality. So to really make it clear how that works, you can add this extra step, which I guess I will since I'm already doing it. I take f of x minus L1, put that part together, and then we add the g of x minus L2 part on the back end. So just kind of get things grouped the way you want. And now guys, this is the absolute value of a plus b. Right, a plus b. So we have our triangle inequality. This is less than or equal to the absolute value of the first one plus the absolute value of the second one. So we can split those off, and sure enough, that's less than epsilon over 2 plus epsilon over 2, which then becomes equal to epsilon, right? So everybody should be able to do a proof like that, right? We did it for sequences, we've now done it for functions. It's pretty much the same idea. In both cases, you've got a triangle inequality as sort of the key crux step to make that argument work. Yeah? Everybody feeling okay with that? Okay, that's the first part. You might remember when we were doing sequences and we did the multiplication one, and so the limit of xn equals x and the limit of yn equals y, then the limit of xn times yn was equal to x times y. You might remember when we did that proof, it was kind of a bit of a headache. It was a little tricky. And the same is going to be true this time around as well. But I'm going to show it to you anyway. Okay. So can I erase this? I want to keep my definition up, but I also don't want to erase my proposition. So this was what was so hard during COVID. I had this little, you saw the little board I was teaching off of for this first 2 weeks. Can you imagine? I mean, keeping all this stuff up for people was so hard. That was the annoying part. It's like, I need a much bigger whiteboard. Anyway, so let's do part 2. Try to prove part 2 here. And I'm going to start off the same way. I'm going to let epsilon greater than 0 be given. And before I actually figure out my delta 1 and my delta 2 and all of that, I just want to take a look. Maybe I will come over here for a minute and do some scratch on this one, because I want to look eventually at absolute f of x, g of x minus L1, L2. Right? That's actually what we need to focus on. We would like that to be less than epsilon. Agreed? That's the whole idea, is to get this thing to be less than epsilon. So you might remember what I did with this when we had sequences and it was like xn, yn minus xy. We did this little trick where we added and subtracted in the middle the same thing. I'm going to do that same trick here. So I'm going to recopy this as f of x, g of x. But then what I'm going to do is I'm going to subtract f of x L2. And then I'm going to add f of x L2, and then minus L1, L2. So in the middle here, I have literally just added and subtracted the same thing. And I'm going to imagine, that I've got my parentheses like this, and I'm going to use the triangle inequality again. Okay, I'm going to use the triangle inequality. So this is less than or equal to, now guys, do you notice on the first part, there's a common f of x factor, f of x and f of x. I'm going to pull it out of that first part. So absolute of f of x times absolute of g of x minus L2. And then on the second term, there's also a common part to this expression, which is the L2. So I can factor out f of x minus L1 and then times absolute of L2. So you would have something that looks like that. That's the scratch work that we're working on here. Okay. Now, just to remind you guys again, we would like this entire thing to be less than epsilon. And just to make it really nice and clean, wouldn't it be great if the first part was less than epsilon over 2 and the second part was less than epsilon over 2? Now I can arrange for the second part to be less than epsilon over 2 fairly easily, because basically remember I can make f of x minus L1 less than anything.
So I can rig that so that it absorbs this L2 that's there. So I'm gonna come back to the main proof right now, guys, and what I'm gonna do is I'm going to find a delta 1 greater than 0 such that if 0 is less than x minus c is less than delta 1, then absolute of f of x minus, I'm gonna put it on the next line, sorry, don't have enough room here. Absolute of f of x minus L1 is less than whatever I wanna put here. And what I wanna put here is something so that the second term will be less than epsilon over 2. So what would that be? Epsilon over 2 times absolute L2, something like that?
Yeah.
So let's just check that out. If f of x minus L1 is less than this, then would you agree that absolute value of f of x minus L1 times absolute L2 would be less than epsilon over 2? Works great, doesn't it? Except that it doesn't quite work. What if L2 was 0? We had this same problem with sequences that if the sequences were converging to 0, then when you do this little thing here, you end up with a 0 in the denominator and it just doesn't make any sense. So there's something we can do though that's an easy fix, which is if the denominator has a potential to be 0, I can just make the denominator a little bit bigger. And that'll have the effect of making this whole fraction even more less than epsilon over 2. Is this okay? I don't want to be dividing by 0. So what do? I just make this my denominator. Okay, because this is less than epsilon over 2. Because you have epsilon over 2 divided by a number that's more than 1. So that only makes the denominator bigger, it only makes the fraction smaller. And we're okay with making it smaller, right? If these two terms are far less than epsilon over 2, so be it. As long as they add up to something less than epsilon, we're gonna win. And we're gonna be happy with the proof. So that's the idea. That is going to be the idea there. Okay, so that is that part of it. Now I have to figure out what to do about the other part of it as well. So the second part, we're gonna have that less than epsilon over 2. But what about the other part? So let's do this. Let's find a delta 2 greater than 0 such that if 0 is less than absolute x minus c is less than delta 2, then absolute of g of x minus L2 needs to be less than, well, whatever I want it to be, okay? So normally what I would do right now is I would put an epsilon over 2. So write this with a light pencil, or don't write it down yet at all, because it's gonna need to be edited a little bit. But I mean, basically this is what you'd love, right? Because if this part is less than epsilon over 2 absolute f of x, then when you multiply the g of x minus L2 by absolute f of x, you'll get your epsilon over 2 again, right? But I think by now you guys are starting to get the idea that whatever we put right here needs to be a constant. It can't have an x in it. In this case, the f of x is in there. So that's kind of the problem. So what we are going to need to do is replace this. I'm okay with that epsilon over 2 there. In fact, let me write it a little bit nicer. I kind of like the epsilon over 2 there, but I need to replace the f of x a little bit. And what I'm going to replace the f of x with is something that's pretty complicated. It's so complicated I'm going to use a -1 exponent on it for a second. And what it is we want to kind of control how big the f of x actually is, right? On this delta neighborhood. On whatever this delta neighborhood is. So, like how big can it get? Well, we can see here that we've already got a delta one. So looking back at the delta one, that sort of tells me, well, how big could f of x actually be, even just based on what we did earlier? Based on what we did here, how big could the f of x be? Well, it has to be pretty close to L1. How close to L1 does it have to be? It has to be within this amount of L1. So you could take this amount and say it could be as much as L1 more than that. Okay? The biggest that the f of x could be would be this thing here plus the absolute value of L1, let's say. And why am I trying to figure out the biggest? Again, the f of x was down here, yeah? That was what we wanted to put. I can't put that there. But what I can put is I can put something down here that's larger than this f of x. That will make the fraction smaller again, just like what I did here. I replaced L2 with something larger than it to make the denominator larger, which makes the fraction smaller. As long as I'm making these fractions smaller, my proof is going to work. So instead of f of x, I want to put something here that will make the fraction even smaller, which means I want to make the denominator bigger than f of x. Well, what's the biggest that f of x could be? The biggest that f of x could be would be this upper bound, sorry, L1 plus this upper bound here. So let's write it down. I'm going to use a -1 exponent on this thing, and I'm going to take my absolute L1, and I'm going to say, hey, the f of x could be as much as that L1 value, and I'm making an absolute value just to make sure that it's a positive. And it could be as much as epsilon over 2 absolute L2 plus 1 right here. So, no, that's not quite parenthesized correctly, sorry. Let's try that one more time. Epsilon over 2 times absolute of L2 plus 1, like so. Still not getting it. This is where the lack of sleep is hitting me. There we go. There we go. That's what I wanted, okay? So I've replaced f of x with something that's bigger than f of x on the bottom. And also this is a constant. This whole thing here is for sure a constant. And also it's not going to be 0. So we don't have to worry that we're dividing by 0 here. And this is with a -1 exponent. It's all in the denominator portion of this, okay? So let's try it. Let's see if we can now take the minimum of our two deltas. So I'm going to let delta equal the min of delta 1 and delta 2. And I'm going to assume that 0 is less than absolute x minus c is less than delta. So with this minimum choice of the delta 1 and delta 2, guys, both of these things are true. This is true, and this is true. We get to use both of them in our proof right now. And we have the scratch work set up for ourselves to use it right away, right? So then, let's see if I can squeeze it right here. Absolute f of x, g of x, minus L1, L2. Right? I'm going straight to the scratch work. I'm not going to retrace the scratch work this time. I'm just going to write it down. Basically, that is less than or equal to absolute f of x times absolute of g of x minus L2, and then plus absolute of f of x minus L1 times absolute L2. So I just replaced the scratch work that we've already done right there. And now I'm going to go to the next step. And the next step is going to be to incorporate both of these inequalities in the appropriate places here. Okay, so this is going to be, guys, this is going to be less than, let's take a look at it, absolute f of x times, okay, guys, right here, g of x minus L2. I'm going to replace that with this whole thing here, epsilon over 2 times absolute of L1 plus epsilon over 2 times absolute L2 plus 1 inverse. Okay. And then plus for the absolute of f of x minus L1, I again will replace it with less than the epsilon over 2 times absolute of L2 plus 1. And that gets multiplied by absolute of L2. It's messy. I do not deny that. It is a messy calculation. But the hope is that if you kind of ignore the epsilon over 2's, everything else that you see in both terms will be less than 1. Like right here, would you agree that if you just ignore the epsilon over 2, the top is smaller than the bottom? Right? Well, if the top is smaller than the bottom, then that's a fraction that's less than 1. And you've got an epsilon over 2 on that. I'm going to put a less than here. So you can replace that fraction with 1. And then you just have the epsilon over 2. I've still got to do plus. Same thing on the first term. I've got my epsilon over 2 right here. My epsilon over 2, I'm literally recopying it. And then what else do we have? This is my numerator. And this whole thing inside the parentheses is my denominator. But didn't we just get done saying that the biggest that f of x could be would be to take L1 and add this much to it? Right? That means that my denominator, which is really what this is, because I've got a negative exponent on it. This is my denominator. It is bigger than the numerator of f of x. And so again, this is correct as stated, epsilon over 2. And so epsilon over 2 plus epsilon over 2 is epsilon. That's your proof. Whew. That one will get you sweating a little bit. It's a bit of a technical calculation. So this part isn't so bad, right? This part saying, look, I need to replace, f of x minus L1 with something that's less than 1 over L2 times epsilon over 2. And that's what this is. The plus 1 here is just to make sure that the denominator is not 0. So this part is reasonable. Where it really gets a little hairier is when you then want to bound the g of x minus L2. It's being multiplied by something that's not a constant. And so you have to sort of say, well, it's not a constant. Well, what's the worst case value that f of x could actually have? And the biggest that it could be based on this first inequality is the part that's inside these parentheses here. So that's the reason that you have to do that. Okay, I'll let you guys stare at that. And I think step 3 I'm going to skip because I'm getting tired. But that's the proposition. That's the proposition. Keep in mind, guys, a lot of this is just mostly just technical stuff to get the proofs to work. If you kind of get the concept of it, like if you understand that you want to use the triangle inequality like this, and that you want each of them to be less than epsilon over 2, and then you can control this part and this part, right? And use whatever they're being multiplied by to sort of make a denominator on your epsilon over 2. That's the big idea of the proof, right? That's actually the idea. And at that level, it's not so bizarre. It's when you really just get in the weeds and you say, I really want to be very technically precise about how big this could actually be, or this part. That's when it gets a little bit technical. So it goes, the technicality ramps up like this, but I don't think that the concept of the proof does. The concept of the proof is really just boom, 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 boom. 4 terms here, and I want to get an epsilon over 2 in both of these 2 terms by just choosing my delta 1 and my delta 2 ahead of time to be what they need to be to make it work. In that sense, it's no harder than the proof of part 1. You guys are smiling like, I don't know if you. Oh, yeah, Dr. Anna, easy for you to say.
You start doing stand-up.
Yeah, right. What's up?
On the top portion of the proof over here, you're multiplying by L2 or L1?
This is L2. It's the same L2 that we have right here.
Oh, okay.
Yeah. That L2 is getting copied here. And so I need this whole thing to be less than epsilon over 2.
So we just
Right?
grab it.
So we, that's why we put that right here. Because we get to pick this thing. We have control over this and this, right? And I chose them in exactly the way that we would need to choose them to make this thing work out with epsilon over 2 and epsilon over 2. That's it. Yeah, Robert?
When you were choosing for that, the top side of that right-hand
This one,
inequality,
yeah.
that's coming from that scratch work that you previously erased.
It is basically, well, it's basically this, because this was the scratch work, is that you have this is your f of x, g of x minus L1, L2. The scratch work was that it's less than or equal to this part, right? And I want this whole thing to be less than epsilon over 2.
And that's part
So
of the
that
triangle
means
inequality.
this part needs to be less than epsilon over 2 L2. And I gotta do that plus 1 thing to make sure the denominator's not 0. A lot of little details.
And then that follows that triangle inequality.
It does, yes,
Or that-
exactly.
that follows.
You're using, yep, for sure. Good question. Okay, let me just, okay, this was a lot of work. Can I do an example of it? I should at least show you an example. Let's suppose I ask you to compute, so compute, we don't need a lot of work for this example. This is pretty quick. Let's compute the limit as x approaches 4 of 2x cubed minus 7x squared plus 61x minus 55. Now, you could probably figure out what this limit is equal to by just plugging in x equals 4 into this. This is a polynomial. So if you plugged in 4 into this thing, you'd get a number, and that would be what it's equal to. But can you imagine proving it from the definition? This is your f of x. You would be subtracting some number from that, so whatever the limit is. But so the 55 will change to some other number. But the rest of it will be the same, and you'll be setting that all less than epsilon and trying to solve for what, absolute of x minus 4? I don't think so, okay? Even the quadratic function that we did last Thursday, where we had to factor a quadratic and we got lucky that the absolute x minus c factored out of the quadratic, even that took a bit of work to solve that one out from the definition. This would be a nightmare to do from the definition. Because I have no idea, if you take that f of x, that is a nasty looking f of x, setting it less than epsilon and then hoping to solve for what x minus c would be less than. In other words, the scratch work part would be horrendous for something like that, okay? But I have a much simpler answer for you now. Okay, let's do the solution here. The solution here is by proposition 4.7. The limit as x approaches 4 of 2x cubed minus 7x squared plus 61x minus 55 is equal to. So limits respect everything. They respect addition, subtraction, multiplication, and products and powers and everything, right? I can think of this as the limit. Okay, I'm gonna write it out. The first time, guys, just this one time, I'm gonna write it out super detailed, okay? It's the limit of 2 times the limit as x approaches 4 of x quantity cubed, right? Minus the limit as x approaches 4 of 7 times the limit as x approaches 4 of x all quantity squared, okay, plus the limit as x approaches 4 of 61 times the limit as x approaches 4 of x minus the limit as x approaches 4 of 55. Now keep in mind that to write all of that down like that, I have to know already that limits respect addition, multiplication, and so on. Actually, in this case, it's mostly, well, and subtraction. There's a subtraction here. So limits are respecting everything. X cubed is really just x times x times x. That's just, it's like f of x, g of x, and h of x are all just equal to x, right? So I can calculate their limits individually and then multiply them together, right? Now, this limit theorem does assume that each of the individual limits exists in the first place. So be a little careful about that. If any of the limits maybe didn't exist, any of these individual limits, then we couldn't use this limit theorem, right? But in this case, the limit of 2, the limit of any constant is just that same constant, right? And what is the limit of x as x approaches c? It's just whatever c is, right? Which in this case is 4. That'd be 4 cubed, right? Then minus, again, we have a constant, so the limit of 7 is 7. The limit of x is just c, which is 4, so that's 4 squared. And then plus 61 times 4, and then minus 55. And I didn't actually calculate what this is. I should have done that, just so we would have a number there. But with a calculator, you can come up with the answer. What you'll notice here is that at the end of the day, what is the answer? The answer is just whatever you got by plugging in the limit value in for x everywhere. So the answer is not surprising, and it's not hard to get, right? We could, you know, be stranded on a desert island, and to get off, we have to figure out what the answer is here. Just plug in 4 for x, and you're going to get the answer, right? But if you want to see kind of, well, how does it actually use the limit theorems, right? Instead of just sort of going across the surface without really understanding it, I do think it's useful to see it at least one time spelled out fully, piece by piece here, if that makes sense. We're going to get sloppier with that, though. Obviously, at some point, we'll start to say, oh, we can just plug in the limit value and we'll be good. So anyway. So far, so good? Okay, well, I've talked a lot about proving that limits do exist and using this epsilon delta definition, and now we're starting to get some tools, these limit theorems being first among them, some tools for actually evaluating these limits without having to go all the way back to the definition every time. But I haven't talked much, what I have not talked much about is, what about when limits don't exist? When they don't exist. One way to prove that a limit does not exist would be to negate this definition. Find a specific epsilon for which every delta fails, right? So does there exist a delta? I don't know if you remember this from your logic class or your proofs class where they negated a statement like this. The negation of for some would be there exists a delta such that, there exists an epsilon such that for all delta, this statement is not true, right? And so you could do that. You can see again, it's kind of technical and it's kind of messy. So what I'm going to do after we take a little break is I'm going to show you a really nice proposition. It actually uses sequences. A really nice proposition that will allow us to disprove that limits exist much more easily than having to negate this definition, which I don't think any of us really wants to do any more than we have to. Okay, but let's take a little break for 10 minutes or so. I think I've gone long enough for now. So roughly 2:15, we'll talk about that that proposition that I was just alluding to. See you back in just a few minutes.
Where were you?
So I did my first year in college, and so I was visiting some.
Oh, nice, nice, okay, cool.
Just being stuck here.
I'm trying to think if I've ever. I've been at an airport before with other students that I've known. But it's usually been something that was.
No, you're just being.
Maybe so.
That's what we're doing.
Oh, I'm so frustrated about that weather I had though.
I felt bad when I read the thing, I was like.
Yeah. But you know, a few years ago, I tried to climb Mount Rainier and we had bad weather and I had to go down to that. And that was a much bigger pill to swallow because that was 4 days of training. It was pretty expensive. This thing I did this weekend was so cheap because my buddy,
Yeah.
I stayed at his house, so he he drove us down there. I didn't have to do anything except get my airline ticket, which
Yeah.
wasn't that bad. So, but when I did Mount Rainier, yeah,
That would have been
was-
like your academic camp.
yeah, it would be like that, and, you know, normally you don't get a refund on these things just because of the weather. I mean, if something happens where they have to abort the climb, then that might be the case, like, I'm talking about if you go with a guided
Yeah.
group, see, I didn't go, this is just with a friend. So when you go with a friend, it's always much more of a low commitment, so. Yeah, and the other nice thing is my friend's already climbed this mountain, so he didn't care.
Yeah.
And I said, well, can we try it again next year? He said, sure, because he likes to just go up on the mountain and snowboard down it. So I'll just go up there next year and try it. I actually would go again next weekend. It's just supposed to snow like 3 feet between now and next weekend. I think it's pretty much gonna shut the mountain down. And if you wait till April, then it's no longer then you have to have a permit, you have to go through a lottery
Definitely
system.
sounding like a next year.
Yeah, I think so. I think that's probably right. Our spring break would be a good time, but our spring break is mostly in April, I think. And again, for April, the whole rules on that particular mountain, they change. So, yeah, you have to have a permit, which you have to apply for and get a lottery. You have to get lucky, they have to pick you in the lottery.
Oh,
So-
gosh, the whole thing.
Yeah, it's a whole big hassle, so. I probably won't bother with that. But I won't say I'm not gonna go hiking again this week.
Oh, I wouldn't.
Most weekends I do. I might take the weekend off and these weekends, we'll see.
Probably should, catch up on some rest.
Some rest? What's that?
I honestly haven't figured it out. It's been about 14 years since I rested.
I figured. I'm probably more rested than you and I've been climbing mountains.
It's probably a lot easier than what I'm doing.
I know, it probably is. I know what you're doing.
Oh.
So did I hear it's supposed to rain again?
Yeah.
Yeah, it was pretty choppy coming in this morning. Is it supposed to start today or not?
Today.
It is today. It's supposed to, so by tonight it's gonna rain. Oh, wow. Jeez, I didn't even, my raincoat is, I literally drove from the airport and I left all my stuff in the car, including my raincoat.
Well, it's a good thing,
What's that?
good thing it's here.
It is here, but I gotta get out to my car. Just parked pretty far away because I came in late. I'll figure it out.
So what?
Is everybody doing all right on the homework for tonight? Still working on it? You're gonna ask me questions though, right? If you have them? don't let me, don't let me sleep tonight. I would rather answer the questions today and then have an easy grading tomorrow. Than to answer no question today and then tomorrow I have to grade and, takes so much longer.
So we were kind of just following along when we were doing homework, we were just like following along with the examples that you did in class.
Okay, if you did that,
It-
if you did that, you should be good.
I know for like 3.4, we did
I know we did examples of 3.4. I know we did examples of 3.7, like all that stuff.
Yeah,
Yeah.
so we were just trying to follow along with what we did. In class. 3.4, 3.7.
Rain's gonna be an hour and a half. Are you staying? Oh, you're still staying in that same place? Yeah. Yeah. Cool. This is nice. Oh, cool. Next semester too? Nice.
Next semester.
Anything to cut down on the commute. Yeah. I don't blame you for wanting to get out of that.
Running the line right up here on that, and tries to, you want to be over all the time.
You're driving, next time. Yeah. I was running over to- But that's what they drive on the-
How was your weekend? Did you do anything? Don't remember the weekend? I guess it is Tuesday already. I always forget that my weekend is really over Tuesday starts.
What are you talking about? We all made flashcards and studied 350.
That's the right answer.
Always.
That's good, that's good. We do have a test coming.
I did make flashcards.
Good, good. So guys, what I put on the board over here, I decided to kind of, because of the way I'm gonna do this next proof, I just, added to this definition. This is also kind of a recap because we put this down before as well, but what I've got here is just another way of talking about the limit of f of x equaling L, but in the language of neighborhoods rather than using the epsilon delta notation. So, you know, when it says for every neighborhood V of L, that's really talking about for every epsilon greater than 0, right? And then there exists a neighborhood U of C. That's just gonna be, that there exists a delta greater than 0, right? So this is just a bunch of words that really can be mathematically translated the way I've got them in the box. For every neighborhood of L, there exists a neighborhood of C such that if X is in the neighborhood of C and in the domain of the function, but not equal to C, that's what all this is saying, then f of x is within the neighborhood of L. Okay, which is just the epsilon neighborhood. So this is just a rewriting or a rephrasing of what's already up on the board there in the box. And I think this should already be in your notes from last week. Just wanted to get it up there again, because I'm gonna refer to this definition in this next result now, okay? So I promised you a proposition that would help us whenever we want to disprove that a limit of a function exists. And it is proposition 4.6. I'm gonna put it right here, guys. 4.6. So let's get this thing stated. What this says is we have the limit as x approaches C of f of x is equal to L if and only if for all sequences xn converging to C. So if for every sequence that converges to C with xn not equal to C for all n. So it's got to be a sequence of numbers that converges to C, but without ever equaling C. Without ever equaling C. So for every sequence of points that are not equal to C, but which converge to C, we have the sequence f of xn. So guys, just as x1, x2, x3, x4 is a sequence, so is f of x1, f of x2, f of x3, f of x4. So that sequence should converge to L. That's the proposition. That's the proposition. Now, this would be a really bad result to try to use to prove that a limit does equal L. Because if you wanted to use this theorem to prove that the limit of f of x is equal to L, what would you have to do? You would have to, oh my gosh, take every possible sequence that converges to C. I mean, how many different sequences do you know that converge to 3? Billions, billions of them. And this is say for all of them. For every one of those sequences, you would have to look at f of those sequences and show that it converges to L. This is not the way to prove that a limit exists. You do not use proposition 4.6 to prove that a limit exists. Instead, what you do is you use this proposition to prove that a limit does not exist. Because all you have to do to prove that the limit of f of x does not equal L is find one sequence that's converging to C for which the image of the sequence does not converge to L. And that is often a very doable thing. So I'm going to show you some examples of using this proposition in a minute. Before I do that, though, I'd like to prove the proposition. Okay, I'm going to prove this proposition first. It is a sequences characterization for the limit of f of x equals L. It is a double arrow. I have to prove both directions here. Let's start with the forward arrow. So I'm going to prove the forward direction. That means I'm going to assume to begin with that the limit of f of x as x approaches C is equal to L. I'm going to make that as my assumption. And then I have to prove that for all sequences xn, blah, 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 right? So let's grab a sequence. So let's let xn be a sequence with xn converging to C and xn not equal to C for all n. So we're going to grab a sequence of inputs xn that are converging to C. And then we need to show that the sequence f of xn, that is a sequence, that it converges to L. So given that the limit of f of x is equal to L, we're gonna prove in the forward direction that the sequence of f of x1, f of x2, f of x3, f of x4, and so on, that it converges to L. That's the idea. Okay, so it's a very short proof here. To prove that this sequence converges to L, I'm gonna make a neighborhood of L, an arbitrary neighborhood. So to do this, let V, so let V be an arbitrary neighborhood of L. Right, so again, let's just remember, what does it mean for a sequence to converge to L? It means for every neighborhood of L, there exists an n naught such that for all terms beyond the n naught term, those sequences, those terms of the sequence are within that neighborhood. Okay, that's basically what it is. So we're starting with an arbitrary neighborhood of L. Now, because we are assuming that the limit of f of x is equal to L, that means we're assuming this, right? We're assuming that for every neighborhood of L, including the one that I've just introduced into my proof, that there already will therefore exist a neighborhood U of C, right? So let's bring that into play. So since the limit as x approaches C of f of x is equal to L, there exists a neighborhood U of C such that all of this stuff over here, if x is in U and in the domain and x does not equal C, then f of x is in L, right? So let's just write that down, such that if x is in U intersect D and x does not equal C, then f of x is in V. But guys, since the xn sequence converges to C, say that somewhere, xn is a sequence converging to C, and notice that the xn's are not equal to C. If the xn's are converging to C, then then we do know that then xn is eventually in U. Again, so for every neighborhood of C, the terms of this sequence will eventually be in that neighborhood. And I have a neighborhood of C already in my proof, right? We've already introduced this neighborhood of C in the second line here. And so here's a neighborhood U of C, and so xn is eventually in U. And so what do we know about that? Well, we know that if xn is in U and xn does not equal C, then f of xn is in V. Right? So f of xn is in V. Okay, so what is special about this neighborhood U that we have? It's that anytime x is in U, then f of x is in V. So here's xn is eventually in U, so then f of xn is eventually in V. And that exactly means, hence, that is exactly what it means for this sequence f of xn to converge to L. How do you prove that a sequence converges to L? You pick an arbitrary neighborhood of L, and you try to show that your sequence is eventually inside of that neighborhood. And that's what we did right here. F of xn is eventually inside of V. And so that means f of xn converges to L. Great, that's the forward direction. That is the first part. It's a little bit wordy, I would say. Because I'm kind of using the wordy version of the definition of limit there, so there's lots of talk of neighborhoods. And terms eventually being inside of a neighborhood, but that's exactly. Coming straight from the definition here. This proof is not doing anything clever, we're just kind of unwrapping the meaning of these terms. It's really what it is. Let's do the backwards direction, which is about the same length. The backwards direction of this proposition, we have to prove it as well. And it's about the same amount of work, I would say. So it's very similar. I'm actually gonna do it kind of by way of contradiction. So to do the backwards direction, guys, I'm gonna assume that the limit as x approaches c of f of x does not equal L. So I'm kind of going in contradiction mode or contrapositive mode, whichever way you want to say it. Okay, so I'm negating this. I'm saying assume that the limit of f of x does not equal L. That's my first line over there. But what does that mean? Well, that means there exists a neighborhood V of L such that for all neighborhoods of C, this condition fails. So let's just write it all out in plain English. So there exists a neighborhood V of L such that for all neighborhoods, U of C, this condition fails. In other words, there's going to exist an x that's in U where f of x is not in V. Right, just add that as well. There exists, again, it's just words that correspond to a definition. There exists an x that is in U intersect D with x not equal to C. Such that f of x is not in V. Well, let's take a breath. I'm assuming that this fails. And so far, everything written on that board over there is just the negation of these words right here. I haven't even used the assumption yet. I haven't even talked about sequences yet. This is supposed to be a proposition about sequences. I don't even have a sequence in the proof yet. So far, I've just said, well, what does it mean if the limit of f of x? And what it just means is that this business with neighborhoods fails. In other words, there exists a neighborhood such V of L such that all neighborhoods U of C have this property that you can find an x in U such that f of x is not in V. It's really what it's coming down to. Okay. So for all neighborhoods of C, you know what? I'm gonna make a whole bunch of neighborhoods of C right now. Every single one of them fails. Right? This neighborhood V has the property that all neighborhoods of C, which I'm calling U, they all fail to have this condition. So let's make a bunch of them. Let's consider the neighborhood U sub n. U sub n is going to be the neighborhood C minus 1 over n to C plus 1 over n. And find some point xn that is in U sub n, but xn not equal to C. So just basically, I just want you to find a point that's in that neighborhood, a point other than C. Right, and this is, I should note here, this is for all natural numbers n. So the n is, of course, indexing a sequence, so this is for all natural numbers n. So there's a neighborhood U1, there's a neighborhood U2, there's a neighborhood U3, there's a neighborhood U4. Each of them, by the way, is getting smaller and smaller and smaller, and we're finding x1, x2, x3, etc. inside these smaller and smaller neighborhoods. What do you suppose that sequence of xn's is going to do? Converge to C. Converge to C is exactly right, because these neighborhoods, right, here's C, right, U1 is here. So you pick x1 in there, right? Then U2 is like half as big, there's U2, so you gotta pick x2 in there. Then U3 gets a little bit smaller yet, you pick x3 in here. What you're realizing is that these x's, they are converging to C, and none of them is equal to C, the way we're choosing them, right? So note that xn converges to C with xn not equal to C for all natural numbers n. Okay, well, but what do we know about the f of xn's? So for every one of these neighborhoods, what's the condition? So for each of these use of n's, we can find xn such that f of xn is not in V, right? So let's just note, for all natural numbers n, f of xn is not in V. That's the condition. And if f of xn is not even in V, let's remember what V is. Here's V. V is just some neighborhood of L, right? Is that what it says up there? There exists a neighborhood V of L. And f of x1 isn't in there. F of x2 isn't in there. F of x3 isn't in there. None of the f of xn's are in this shaded interval here. Doesn't that tell us that the f of xn's are not converging to L? They can't possibly converge to L because they're not even in the neighborhood that's this entire interval around L. This is just some fixed neighborhood of L, right? And f of x1 is outside of it. F of x2 is outside of it. F of x3 is outside of it, right? It's like a fenced off area. The f of xn's can't get into that shaded region, so of course they can't converge to L. And what we have done now, guys, what we have done is we have made a sequence of xn's that converge. This is our proposition, right? This is what we're proving. I started off with the negation of this. And what am I ending up with? The negation of this. I have made a sequence, xn, that converges to C, but for which f of xn does not converge to L. So this part of the proof, if you want, you can think of it as by way of contrapositive or contradiction, either one, but I'll say contrapositive here because I didn't really assume it. That I was doing it by way of contradiction. So we'll just say by way of contrapositive. That is how we've done that proof. Okay. So it's a little bit of work to kind of get all the words here and all this talking about neighborhoods and so on, but that is the proof of this proposition. Any questions so far? Well, I want to have some fun then. I want to have some fun with the proposition. I said that we don't use the proposition to prove that limits do exist because you can't possibly hope to prove for all sequences that something happens. But we use this proposition to disprove that limits exist. So let's see if we can do it. And I know we've had a lot of proofs and a lot of theory today. Let's see if we just have a little fun with some examples to kind of wrap things up here. So let's do some applications. Okay. So let's, number one, let's prove that the limit as x approaches 0 of 1 over x does not exist. So earlier today, we proved that the limit of 1 over x as x approaches c is equal to 1 over c. That was our warm-up problem. But if the c value is actually 0, then this limit does not exist. So in other words, I'm gonna try to prove that this is negated, and I'm gonna do it using sequences. I'm gonna make a sequence that converges to 0, right? C is going to be 0, but for which the image of that sequence is not converging to anything. Right, that's gonna be the idea. So this is very short. The nice thing about these applications, guys, is that the proofs are very, very short. So can somebody give me, what's your favorite sequence that converges to 0? 1 over n, that's mine as well, thank you. 1 over n, where n is a natural number, okay? So here, we already can see clearly that xn converges to 0, that's good. And xn does not equal 0 for all natural numbers n. So all of this first line is true about my sequence, right? But what is f of xn? So actually, I didn't really reference an f of x here. The f of x is just 1 over x. That's what this is referring to right here. It's obviously the function we're taking the limit of. So what is f of xn going to be? It's going to be 1 over xn, and 1 over xn is 1 over n, which is n. Yeah, and that is not even bounded. If it's not bounded, it can't converge, right? So which doesn't converge at all to anything. It doesn't converge. And so by the negation of this proposition, right? So this part on the right is false. The part on the right is false. We've created a sequence converging to C, but the image of the sequence does not converge to anything. If you wanted, you could think of it as proof by contradiction as well. You could say, well, suppose that this limit did exist, call it L, and then you prove that this f of xn is not converging to L. Okay, but it's basically the same as what I've already written here, and this is the end of the proof. So we are done by proposition 4.6. So 4.6 is the way to go when you're disproving that a limit exists. Let's try another one, unless there's a question here first. These are all pretty quick. Let's try another one. This one is also pretty fast. Let's prove that the limit as x approaches 0 of x over absolute value of x does not exist. Okay. Now, by the way, if you wanted to think about that function, x over absolute x, this is just a piecewise function. It equals 1 if x is positive, and it equals -1 if x is negative. So the graph of this function is something like this, right? And so you can kind of tell that this limit is not going to exist at 0. The way to prove that is going to be, again, to try to make a sequence here. So I need to make a sequence xn. This is actually the only part of this that's kind of tricky, is you have to come up with the sequence. You just need one. You need a sequence that converges to 0 On the first warm up, it was real easy. The first problem was really easy because 1/n is everybody's first thought about a sequence that converges to 0. In this case, if we just use 1/n, if you just use 1/n, what we have to realize is that 1/n is always positive, and so we're only gonna be looking at the right-hand half of the graph. And if I only looked at the right side of this graph, the limit would exist. It would be called a right-handed limit. You probably remember from calculus, you talk about right-hand limits and left-hand limits, right? What's really the power behind this example is that we want to use both the positives and the negatives. Because that's why this thing is failing to have a limit at 0, is because there's a gap right at 0. And if I don't work on both sides of that gap to really exploit that, I'm probably not gonna be able to get my contradiction. So I'm wondering if anybody, based on my little bit of rambling here, if anybody has a suggestion for what I might wanna let xn equal. Say it again? How about that? How about -1 to the n over n? It's very similar to 1/n. The only difference here is I'm flipping positive, negative, positive, negative, positive, negative. And that's going to be having me flipping from the top line to the bottom line as I go back and forth, right? That's exactly right. This does still converge to 0, guys. This does converge to 0, and we can still say that the xn is not equal to 0 for all n in the natural numbers. That's absolutely still true. Same as with the first example. So there's nothing different there. But let's look at f of xn. F of xn. Again, the f of x is just the function that we were given there. This is xn divided by absolute xn. In other words, it's -1 to the n over n divided by the absolute value of -1 to the n over n. And what you'll notice about this, guys, is that the n's will cancel. The -1 to the n on the bottom will become +1. So the only thing that actually needs to be kept track of is in the numerator, you have a -1 to the n. Everything else is basically canceling or becoming 1. And now, does this converge? It was one of our very first examples of a sequence that does not converge, right? So let's just say, which does not converge? Which does not converge? All right. So we're done by proposition 4.6. Yep, we are done by proposition 4.6 again, same exact thing. All right. Questions on this? So the use of this proposition is generally you're gonna have to create the sequence. That's gonna be the tricky part. And it's gotta be a sequence that's converging to C, right? It has to converge to C, but when you look at F of your sequence, the images of your sequence, somehow it's not converging. Let's do one more. And this time I'm gonna let you guys try. I'm gonna be quiet for a couple minutes and let you guys try it. Let's prove that the limit as x approaches 0 of the sign of the quantity 1/x does not converge. Let's try to prove that that one does not converge. So this time, I'm gonna give you guys a minute or two to think for yourself. You can talk to the person next to you if you want to, or just think about it quietly, either way. How could you make a sequence that would demonstrate that this doesn't converge by using that proposition? needs to be a sequence that's going to zero. It'd be nice if it was xn values that are easy to evaluate here. You don't want to get messy. We don't know sign values very well off the top of our head, so it'd be nice if those numbers were easy to work with. Oh, by the way, does everybody know what this Friday is? It's Pi Day. Okay, oh, I just thought I'd mention that. Does anybody have a sequence that they're trying to work with yet? You know, I also, maybe I should make another comment here, because this one is actually going to work slightly differently than the ones we've already done. Another way to do this is to actually do two sequences, both of them converging to zero, but such that f of the first sequence, maybe it's not that it doesn't converge, but maybe it converges to something different than f of your second sequence. Right. So what I'm thinking of here, I don't know if did anybody think of trying like 1 over n pi? Did you? Yes, because the nice thing about this is it's converging to zero, and if you plug it in here, you just get sine of multiples of pi, which are all just zero. Right, so this is definitely converging to zero, and xn does not equal to zero for all n, right? All of these assumptions are true. Okay. And here, if we look at this, f of xn would be the sine of 1 over xn, which would be the sine of n pi. Sine of n pi is actually 0 for all n. So I'm not getting a contradiction like I did here. I got an expression that didn't converge. Or here I got an expression that didn't converge. This time I got something that does converge. This obviously is just 0, 0, 0, 0, 0. It definitely does converge to 0. So at this point you might be thinking, I wonder if L could be 0. I wonder if the limit could be 0. Because we have a sequence that's confirming it right here. Of course, it's not. This work alone is not proof that the limit is equal to 0, because to prove that the limit was equal to 0 using sequences, remember, you would have had to check every sequence under the sun that's converging to 0, which would take a lifetime, right? So this is just checking one sequence, and we're getting that it converges to 0. But you know what I'm going to do right now? I'm going to make another sequence. I'm going to make another sequence. And my second sequence is going to be the following. It's a little messier. It's going to be 1 over 2n pi plus pi over 2. Let's try this. Now again, as n gets larger and larger and larger, that denominator blows up. So this is going to converge to 0. Okay, and again, we can certainly say that yn does not equal 0 for all n. But let's take a look at f of yn. F of yn, that would be the sine of 1 over yn. And the reciprocal of yn would be just the 2n pi plus pi over 2. So these are multiples of 2 pi with a pi over 2 added to them. Does anybody remember their trig values. What is the sine of pi over 2? It's 1, right? Sine of pi over 2 is 1, and what happens when you add 2 pi to the sine function? It just repeats itself, right? Adding 2 pi to the angle doesn't change the sign at all. So these are all equal to 1 for all n. So this is a sequence of 1, 1, 1, 1, 1, 1, and that's a constant sequence that converges to 1. So in this example, guys, I did not come up with a single sequence that failed to converge. What I did instead is I made 2 sequences that converged to 2 different values. And so what is L? If L was 0, then this would contradict that. If L was 1, this would contradict that. And if L was anything else, either one of them would have contradicted it. There is no L, right? That is basically the point here. So no limit, so no single value of L is possible. So this example illustrates another strategy for using the proposition, which is to create 2 sequences that are both converging to C, but whose images, maybe it's not that they don't converge, but they converge to 2 different values. That has to be a contradiction. That has to be a contradiction. Yeah, so that is it. That's a nice way to do that. Robert?
For that, the second part, the y of n, I was like initially thinking, for that function, it could be if it's a 2 and pi, it could just be n pi over 2. Or would I kind of just run into that same problem of having a 0 and 1?
N pi over
You
2.
still hit both values, or that is kind of running.
Get the 2 rotation that you need, you might get a 3 rotation or a 4 rotation, and you'd be back to 0.
What was your question?
How about I just do like, 1 over n?
What, 1 over n?
That's fine.
Okay, if, so you could also use 1 over n, because the sine of n is a sequence that diverges. I think you did that as a homework problem. So you could have done it that way as well, yeah, using just 1 over n. But I wanted to illustrate here that you can sometimes do it with 2 sequences. And Robert, you absolutely could use different sequences instead to illustrate that. Yeah, so there'd be more than one way to do it. Anyway, I've got to let you guys go. Thank you for today, guys. I will see you all on Thursday, if not my office hours before that. Bye for now.